Good morning to one and all. Welcome to my channel fields-10. Today we discuss electric charges and electric field lesson 12th standard first lesson. In this one 10th video, see torque act on an electric dipole when placed in uniform electric field. Electric dipole is placed in uniform electric field. What is the torque act on the electric dipole? For that we can derive an equation and related problems we can do. See here, first we discuss uniform electric field. Uniform electric field means electric field lines parallel to each other. Electric field lines are parallel to each other and straight line and are equispaced. Thus that electric field we call it as uniform electric field. See, uniform electric field means electric field lines are parallel to each other, straight line, equispaced. That electric field we call it as uniform electric field. See, in this one, for example, here we can take one point, here one point we can take, here we one point. See, electric field at A point, which is equal to electric field at B point, that is equal to electric field at C point. Means every point, this point or this point, this point, electric field is same. That electric field we call it as uniform electric field. See, electric field means we know a region around a, means the space around a charged particle within which a force is exerted on the other particle is called as electric field. See, that electric field is a vector quantity that we can write E equal to kq by r square. For this, what now we can write, force per charge, test charge, is called as electric field. Force per test charge. See, electric field now, what is the unit now? Newton per coulomb. Newton per coulomb is the unit of electric field. Its dimensional formula is m l t power minus 3 a power minus 1. This is the dimensional formula of electric field. See, for example, here a charged particle is placed q. What happened now here? See, a force is exerted on the charged particle. See, what is the actually electric field equal to what? F by q. See, QE changes to here now QE. What is the force acting on the charged particle now? QE. See, positive charged particle now electric field is in the direction, means force is acting in the direction of electric field. See, a charged particle is placed in the electric field. A force is exerted. That is, for example, here positive charge now force is in the direction of electric field. Negative charge now force is opposite to electric field. That is QE. QE. See here. So that is the force exerted on the charged particle when it is placed in the electric field. Uniform electric field na this is. So this one in this direction, this one in this direction. Positive na in the direction of electric field, negative na opposite to electric field. See here, in this case we discuss one more. What is that electric dipole? Electric dipole means it is the, means two equal charges, two equal and opposite charges which are separated by a small distance. See, two equal, so means plus q minus q, two equal and opposite charges which are separated by small distance 2l. This is called as electric dipole. See, two equal and opposite charges which are separated by small distance 2l is called as electric dipole. For example, it is the center. This distance is L. This distance is L. See, 2l. So total is distance between the charges is 2l. So means electric dipole means two equal and opposite charges which are separated by very small distance, so that is 2l, so that we call it as electric dipole. So electric dipole moment, see, electric dipole moment represented by letter P. See, it is always negative charge to positive charge. Electric dipole moment is negative charge to positive charge. What is the electric dipole moment now? Product of charge and its length is called as electric dipole moment. Means P equal to Q into 2L. What is its unit now? See here, coulomb meter is the unit of electric dipole moment. Electric dipole moment. Electric dipole na two equal and opposite charges which are separated by small distance 2L is called electric dipole. Electric dipole moment is minus q2 plus q is there. That electric dipole moment is p equal to q into 2l. So what is the unit now? Coulomb meter is the unit of electric dipole moment. Electric dipole moment. For example, see coulomb na we can write current into time. So a t length na l. So l power 1 a power 1 t power 1 is the dimensional formula of electric dipole moment. Electric dipole moment. L means length, a means current, t means time. So l power 1 a power 1 t power 1 is called means dimensional formula of electric dipole moment. So electric field na mlt power minus 3 a power minus 1 mlt power minus 3 a power minus 1 dipole moment na lat. This is the dimensional formula. Unit is coulomb meter. See next, what important here? Torque. So torque means it is the tendency of force it rotate a body about its axis is called as electric sorry torque. Torque is the tendency of force which rotate a body about its axis around its axis, that is called as torque. So torque how to represent? Not tau. So tau equal to force into perpendicular distance. Force na newton, distance is meter. Newton meter is the unit of torque. It is a vector quantity. See what is the dimensional formula na here? M l power 2 t power minus 2. This is the dimensional formula of torque. See here three terms we use. One is torque, electric dipole, and uniform electric field. See uniform electric field na F by Q, Newton per Coulomb. So dimensional formula is mlt power minus 3 a power minus 1. Another term is electric dipole. Electric dipole means two equal and opposite charges which are separated by small distance is called as electric dipole. Here electric dipole moment. So P, this direction is minus Q2 plus Q. Q into 2L is the magnitude of electric dipole moment. What is the unit now? Coulomb meter. So dimensional formula is L A T power 1. So L power 1, A power 1, T power 1. See torque we can use. Torque means force into perpendicular distance. Force na Newton, perpendicular distance is meter. See Newton meter is the unit of torque in SI system. So what is the dimensional formula? M L power 2 T power minus 2. These are the terms used in this deriving the torque exerted on electric dipole when it is placed in the uniform electric field. Uniform electric field. For example, see uniform electric field. See this is the uniform electric field. Yes, so this is the uniform electric field. In this one, we place an electric dipole. Electric dipole has two poles. One is minus Q and plus Q. See here, it is the two equal and opposite charges which are separated by small distance. See, this is the center. Here, center to this charge is L, center to this charge is minus Q is L distance. It is separated by 2L distance, which is placed in the uniform electric field. What happened now here? Two forces are acting. This is plus Q. Plus Q means force is acting in the direction of electric field. See, force is here. This is the force acting on the this one QE. So this is we can write it as F1 force. See here also one more force is acting minus Q, that is QE minus QE we can write. So that is F2. See F1 and F2, two forces acting on the electric dipole when it is placed in the uniform electric field. Uniform electric field. Why we are saying uniform electric field na? So different is there. This two na, here force is different, here force is different, but here both are in equal magnitude. So what is the net force acting on the electric dipole na? See here, F net equal to F1 plus F2. F1 is QE and F2 is minus QE. Why now? It is opposite to electric field. So minus Q charge. What is the electric force acting on the minus Q na? Minus QE. So that is here minus QE. So what is the net force here na? F net equal to 0. So F net is 0. Whenever electric dipole is placed in the uniform electric field, F net is always 0. F net is always, it is always 0. Always 0. F net is always 0. But here see, two equal and opposite forces which do not have same line of action and rotate the body about its axis, about its center of mass, then it is called as a torque. See, I write here two equal and opposite forces, which do not have same line of action, which do not have same line of action, and this body rotate about its center of mass, and rotate about its center of mass, rotate about its center of mass at O, means center of mass. See here, so means this object spinning motion, it has spinning motion, because why? Because this force is acting, means here this direction, this direction, this is this direction, both are in not same line of action. See, this will be this direction, this will be direction, both are in different direction. See, both are in different direction and not same line of action. So that's why it act torque on the object. So that torque is here, in this case torque is clockwise, this is the tau 1 we can say, in this case torque is here tau 2 we can say. So it means two torques acting here, so upward one torque, so downward one torque. So this torque means two equal and opposite forces which do not have same line of action, so rotate about its center of mass, so that will not, this it has a spinning motion, so this is due to torque. So torque equal to force into perpendicular distance, force into perpendicular distance. See here, perpendicular distance means this is the mass here, this is now perpendicular distance. So this distance into what is the force acting here, QE. So force into this perpendicular distance, we call it as torque. See, because of torque, this electric dipole is rotating in the electric field about its axis, or about its center of mass. See here, two torques is there, one is in clockwise direction, this direction, here torque is acting downwards, this side torque upwards. So what happened, it will be moving like this, so rotating like this. So why not, these two are equal and opposite forces but do not have same line of action, because of that torque is acting in this one is downwards, here upwards, but both are in same rotation, means it is called clockwise, here also clockwise, that's why it will be continuously rotating about its axis or center of mass, See here, total torque, now torque means what we can write here, force into perpendicular distance, what is the force now here, QE, here force is QE, here plus QE, here minus QE. So means that is indicates opposite direction only, opposite direction. See, torque is here T1, here torque is T2. So perpendicular distance now, this is the perpendicular distance, but see here electric field, this one, this is the electric dipole which makes an angle theta here. So means electric dipole makes theta with the electric field, so that's why here theta na, here also theta, it has two components, this length has two components, one is L cos theta, L sin theta, here we call it as L cos theta. Why? Because which side theta is there, that is L cos theta, opposite is L sin theta, this is the L sin theta. See here, for this is now here, this is the perpendicular distance, for this minus q. See, perpendicular distance here makes an angle theta, it is L cos theta, it is L sin theta. Here this also has two components, one is which side is theta, that is L cos theta, opposite L sin theta. See what is here, force QE, torque now we have force into perpendicular distance. Here perpendicular distance means distance between plus q and center of mass, perpendicular to center of mass or axis of rotation, distance between force and perpendicular and axis of rotation, axis of rotation, that we can take it as perpendicular distance, distance between force and axis of rotation, distance between force is acting, axis of rotation, perpendicular distance. So this distance we want, that's why we have here L cos theta, L sin theta. L sin theta is the perpendicular distance. See what is the total torque acting on the electric dipole now here. See, T tau 1 plus tau 2, here upward is 1 plus q tau 1, so minus q tau 2. See here tau 1 downwards, here tau 2 upwards, both are in same direction, so clockwise direction, that's why we can add. See here, total torque equal to tau 1 plus tau 2. See here, tau 1 na here force into perpendicular distance. What is the force? QE, perpendicular distance is L sin theta. I write here QE L sin theta. So tau 2 na, see tau 2 here, this one tau 2 na force is QE, perpendicular distance is L sin theta. So QE is L sin theta, QEL sin theta. So to add na total torque equal to 2 QEL sin theta, 2 QEL sin theta. Here now we know before electric dipole moment, what now? Q into 2L. See, this will be write it as Q into 2L into E sin theta we can write. See, Q into 2L na electric dipole moment, so tau equal to P E sin theta. Here P means electric dipole moment, E means electric field, theta means angle between the electric field and electric dipole moment. Electric field and electric dipole moment. Theta is the angle between electric field and dipole moment. Dipole moment. See, whenever electric dipole is placed in the uniform electric field, two equal and opposite forces are acting which do not have same line of action. See, this is one force, this is another force. Both are in not same line of action. Same line of action means this is same line of action, but it is, so both are in opposite. So means not same line of action. So that this not same line of action, that's why that body or object or electric dipole rotate about its axis or center of mass. Center of mass, in this case torque is acting here upward, one torque T1 tau 1, so that is downwards. So here on minus q torque is tau 2, so upwards, both are in clockwise direction. So we can add, what is the total torque now? Tau 1 plus tau 2. Tau 1 is QE, force is QE, distance is L sin theta, perpendicular distance is L sin theta, QE L sin theta. So added to QE L sin theta, Q into 2L. So we can write dipole moment. So that is, we can write P here, E sin theta. Theta is the angle between electric field and electric dipole moment. This is the direction of electric dipole moment. Dipole moment. See, dipole moment this direction, electric field is this direction. See, this will be, so P to E. So object means dipole is moving, rotating, P to E. So that's why, so we can write here, what is the total torque now? P sin theta can be write it as P cross E. Why na? Electric dipole moment is vector quantity, electric field also vector quantity, they resultant also vector quantity. That case we can write P cross E means here, see, P to E, E to P na, so anti-clockwise, so it is wrong. So that's why we can write, so P cross E. So tau equal to what? P cross E means electric cross product of electric dipole moment and electric field. This is the torque produced on the electric dipole when it is placed in the uniform electric field. Whenever an electric dipole is placed in the uniform electric field, torque is active. Non-uniform electric field na, here force is different. So that's why, so means not equal forces. Whenever equal, two equal forces acting on the electric dipole which do not have same line of action. See, this will be different, this will be different, same line of action, do not have same line of action, then only torque is acting on the dipole, then it rotates about its axis or center of mass. So that's what is the torque acting on the electric dipole na? T tau equal to P cross E, or we can write Pe sin theta. When this torque is maximum, when this torque is minimum, so that we find out here. See, for example, see here, when this torque is maximum, see what is the torque now here? So when is this torque is maximum? Maximum na, see torque na, so Pe sin theta, Pe sin theta. See here, theta is maximum, sin theta is maximum Sin theta is maximum at 90 and 270 only. 90 and 270. Sin 91, 271. So the two cases torque is maximum. See here, tau equal to PE. We can write what is the torque na PE. When theta is 90 degrees means electric field na. This is the electric field. See, electric dipole placed minus q plus q is perpendicular to electric field. See, electric dipole is perpendicular to electric field. So this case torque, what is the maximum torque acting on the electric dipole? Electric dipole is placed in the uniform electric field. That case when the maximum torque is acting on the electric dipole na, so this case means angle between the electric dipole moment, this is the dipole moment, minus q to plus q, upward direction, and electric field is this direction. In between these two angle is 90. That case torque is maximum. So one more case, what is that? Now this is the electric field. Electric dipole moment is downward. See, this is minus, it is plus. So electric dipole moment is this one. See, this is the case 0 parallel to electric field. This is 90, this is 180, this is 270. This is the case here. So angle between the electric field and electric dipole moment is 270. These two cases torque is acting maximum on the electric dipole when it is in the uniform electric field. Means P and E means electric dipole moment and electric field are perpendicular to each other, perpendicular to each other, perpendicular to each other. That case torque is maximum. So means what is that case now? Theta equal to 90 and 270. Theta equal to 90 and 270. These two cases torque is maximum and the electric dipole is placed in the uniform electric field. See, now when is this torque is minimum? When is this torque is minimum? See here, it has, so what is the torque now? Torque is Pe sin theta. When electric dipole is placed in the uniform electric field, what is the torque act on the electric dipole now? Tau equal to Pe sin theta. So sin theta value when minimum? Sin theta is minimum at 0 and 180 cases. Both cases only theta is minimum. So for example, see here, it is the electric field. Electric field here. So means electric dipole is placed here. It is plus q, it is minus q. It is the electric dipole. See the dipole now here. See, in this case, what is the force acting on a plus q in the direction of electric field? QE. Minus q opposite to electric field, QE. Both are acting, two equal and opposite forces acting on same line of action. Here see, here both are not in same line of action. So torque is acting here. So in this case, both are acting on same line of action, equal and opposite forces acting on same line of action. That's why net torque is 0. Here net torque is not 0. Net torque is here tau 1 tau 2 we can write, but in this case, so torque is 0. Why? Because this is the force, this is the force, both are in same line of action. Whenever two equal and opposite forces are acting on same line of action, net torque acting on the electric dipole is 0. That's why torque is 0 here. So F net already 0, F net is already 0, torque also 0. This case electric dipole is complete equilibrium. Electric dipole is in complete equilibrium. Again listen. So when is this torque is minimum now? Two cases. One is theta equal to 0 and theta equal to 180 case. Theta equal to 0 means electric dipole is along the electric field. That case, see two forces acting, QE and minus QE, both are in equal in magnitude, opposite direction, and these two forces are in same line of action. Same line of action means F net equal to 0 and torque equal to 0, both are 0. So F net is always 0, torque also 0. Why? Because both are in same line of action. So this case, no torque is acting in this one. This one, in this case, see here, if you slightly displace, what happened? It will get its original position. That's why we can say that this case we can call it as stable equilibrium. Equilibrium, stable equilibrium. See, slightly displace. So which above means it will be displaced slightly like this here now plus q, here minus q is there. What happened now? Here torque is acting and again it will get its own position. Means electric field always tries to get its own along its own axis, along its own axis. See here I write electric field always tries to along its own axis, along its own axis. That's why here see electric dipole is when it's slightly displaced again it gets original position. So mean this we call it as stable equilibrium. Stable equilibrium. See one more. See this is the electric field. See electric dipole is opposite to electric field. See this is electric dipole, here minus q, here plus q. See on plus q force is this direction, this direction. So minus q opposite to electric field. Here see this also we call it as here net force is 0, net torque also 0. So F net equal to 0, torque net torque equal to 0. Why not? These two are means two equal for that. This is QE minus QE, this is plus QE. Both are in the same line of action. So net torque is 0. So, but here, if this is in complete equilibrium, in the same way, if you slightly displace, what happen now? For example, see, it will be displaced here plus Q, here minus Q. It does not get its original position. It changes its own axis along its means electric field always tries to play place or keep along its own axis, keep along its own axis. That's why electric field means here two equal forces acting, here minus QE, here plus Q. These two equal and opposite forces here along axis. That's why what now it will be in complete equilibrium, but here it will be slightly displaced, it does not get its original position. So that we can say that unstable equilibrium, unstable equilibrium, unstable equilibrium. Here stable equilibrium, see we can displace again it gets original position, but here not stable equilibrium, unstable equilibrium. That's why we can slightly displace and not gets its original position. Again it means which direction we are applying, that direction moves under align its own axis, means align along the electric field. So that we call it as here unstable equilibrium. Unstable equilibrium means when is this torque is minimum now, theta equal to 0 case, and the one is theta equal to 180 case. Theta equal to 0 case we can say that stable equilibrium, theta equal to 180 case we can say that it is unstable equilibrium. Unstable equilibrium. Here we can apply slightly force now, what happen now, slightly displaced, it will get it will arrange its own axis along its electric field direction. So electric dipole is moving or placing along its electric field direction. That's why we can say that it is unstable equilibrium, it is the stable equilibrium. This is the when is the torque is maximum na, theta equal to 90 and 270. When is this torque is minimum na, theta equal to 0 case, stable equilibrium, theta equal to 180 case. So unstable equilibrium. See here this case torque and force both are 0, net torque and net torque is 0. See, means net force is always 0, but torque is may or may not be 0. So some cases not 0, this case not 0, this case is 0. So why now? So means whenever two equal and opposite forces which do not have same line of action, that case torque is acting, net torque is not 0. So both are in same line of action, that case net torque is 0. So net force is always 0. Net force is always 0. So this is the torque when electric dipole is placed in the uniform electric field. So torque is exerted on the electric dipole. The torque is P sin theta, or we can write it as P cross E. P cross E. So according to this we can do the problems. See first problem. What now here see, this is the electric field, uniform electric field. Here electric dipole is placed. See this is the electric dipole, it is minus q, it is plus q, it is the center of mass. So this length is L, this length is L. See here it makes some angle theta, so that is 30 degrees. This case see just at the moment, what is the problem now, just at the moment electric dipole is released. Electric dipole is released in the electric field, uniform electric field. Then find angular acceleration. Angular acceleration of dipole, electric dipole. This is the problem. See, just at the moment electric dipole is released in the uniform electric field, what is the angular acceleration that we want to find out. For that, see here, see, torque equal to P e sin theta. Torque equal what here? P e sin theta. See, P means electric dipole moment, E means electric field. Theta is the angle between the electric field and electric dipole moment. Theta is the angle between electric field and electric dipole moment. Electric dipole moment. This case, here see, so torque one we can write another way, that is I into alpha. Means here I means moment of inertia. What na? Moment of inertia. Moment of inertia. So alpha means angular acceleration. Angular acceleration. So moment of inertia na, see this charge q has mass and center of mass. See center. So center of mass. In between them some length is there. So means the product of mass and square of its length between the axis and the mass of object. So that we call it as moment of inertia. Means moment of inertia I equal to, see, this particle mass and distance between the particle and the center of mass, what na distance here L, so square, see ml square. So this particle mass m and length is L, see ml square. Means moment of inertia is the product of mass of particle and the square of the distance between the particle and the center of axis, center of or axis of rotation, or center of mass. So that we call it as moment of inertia. Means a mass into distance between the point and center of mass, square of the distance between the point and center of, that we can write ml square, ml square. What is the moment of inertia now? This one 2ml square. Moment of inertia is 2ml square. Angular acceleration now here we can write it as alpha. So that only we find out here. See, torque means what? P is sin theta. So torque is another way we can write moment of inertia into angular acceleration. Moment of inertia into angular acceleration. See here, so torque equal to Pe sin theta. So instead of torque we can write I alpha. I write here I alpha equal to Pe sin theta. I means what? 2ml square, 2em L square, and alpha that equal to P means Q into 2L into E sin theta. See, L cancel, what we get now here? See, 2ml alpha, 2ml alpha equal to 2Q E sin theta, 2QE sin theta. Theta is what here? Angle between the electric field and electric dipole moment. So that is theta na, that is 30. So 2QE sin 30, here 2ml alpha. See, sin 30 na 1 by 2, 2QE sin 30 1 by 2. Here, see 2ml alpha, this 2 cancel. What we get now? 2ml alpha equal to QE. See, from that we can write, see, alpha equal to what now here? 2ml changes this side. So means QE by 2ml. What is the angular acceleration of the electric dipole when it is just released in the uniform electric field? What now here? Alpha equal to QE by 2ml. Q means charge of the particle, E means electric field, M means mass of the particle, and L is the length between the center of mass to particle plus q, or charged particle. So that is alpha equal to QE by 2ml. See once again this one. See, just at the moment electric dipole is released in the uniform electric field. So find the angular acceleration of the dipole. So that case What is the torque acting on this one? Pe sin theta. Torque we have one more with moment of inertia and angular acceleration, that is I alpha. I means moment of inertia. Moment of inertia means mass into square of the distance between the particle or point into distance axis of rotation. So what is the length between the point and the center of mass? Length na? So that square of this length means mass into square of the length. So means mass into square of the length. Length is what? L, distance between the axis and this point mass. So what we can L here to ml square. So this charge na, this particle to axis of rotation ml square. So what is the moment of inertia? 2 ml square. So moment of inertia means moment of inertia is the product of mass and what is the distance between the mass and axis of rotation. So that distance square of the distance between mass and axis of rotation. So ml square. So here this particle ml square. So 2 ml square. So that's why what is the moment of inertia? 2 ml square. Again repeat here. So this one from this axis of rotation to this plus q. What is the distance L? So and this plus q has mass m. So m into square of the distance between them. So that ml square. So this one, this minus q, mass is m and distance between them is L. So square of the distance, mass into square of the distance between them. So ml square, ml square, 2 ml square. So what is the moment of inertia of this electric dipole moment na? Electric dipole. So 2 ml square. See what is the alpha na? Angular acceleration, I alpha. I means 2 ml square into alpha, that equal to q. P means charge into distance between the electric dipole. So that is q into 2l e sin theta. See this L cancel, 2 ml alpha equal to 2 q u e sin theta. So here sin theta na 30 degrees. Why na? Here electric field, it is electric dipole. So electric dipole and field now what is the angle? 30. We can write sin 30 1 by 2, 2 to cancel QE. So 2 ml alpha equal to QE, alpha equal to QE by 2 ml. What is the angular acceleration of the electric dipole when it is placed in the uniform electric field at an angle of 30 degrees na? So what na is alpha equal to QE by 2 ml, 2 ml. See next na, here see one more problem, that is if the electric dipole is slightly displaced from its equilibrium. For example, see here I will take, see the uniform electric field, this is the uniform electric field. See in this one here electric dipole is there, minus q and plus q. See this now it will be slightly displaced. For example, it will be like this displaced, this plus q, it is minus q, it is slightly displaced with a theta angle. This case what happen is one, it will oscillate with a small frequency. That case what is the time period of that oscillation of the electric dipole, that we find out. I write here, if we displace, if we displace the electric dipole from stable equilibrium, it oscillates small frequency, then find time period of electric dipole or oscillation, means time period of its oscillation, time period of oscillation. See what now here actual electric dipole is there like this, it will means slightly displaced. What happen now, it makes some angle, that case it will oscillate to and fro. So that case now what happen now, here simple harmonic motion will just, so means it will oscillate with a small frequency. That case what is the time period of that oscillation we find out. For that here see we can write what is the torque when slightly displaced. Now torque is acting on this one. So why not two, here one force acting, here one force acting, these two forces which are not in the same line of action, that's why torque is acting. Because of torque it will be oscillating like this. So now, so that case, what is the torque acting on this one now? Pe sin theta. Here theta is very small. Theta is very small. That case we can write sin theta equal to approximately equal to theta. So that means tau equal to what we can write? Pe into theta. See here, this electric dipole is means displacing this direction, torque is acting this direction. Both are in opposite direction. Torque will be this direction. So means this will be displacing. Angular displacement in theta is this direction. So that's why we can take here minus theta. Why now? We know already in simple harmonic motion, force is directly proportional to minus x. Minus x. So that's why here we can take P equal to minus of theta, minus of theta, we can write it here. Now we know torque equal to what? I alpha, moment of inertia into angular acceleration. So means I alpha equal to Pe minus theta. So means alpha means angular acceleration minus of omega square theta. So why not? Displacement is opposite to force acting or torque acting. That's why we can write minus omega square theta. Instead of alpha we can write minus omega square theta, that equal to Pe minus of theta. See here, I omega square into minus theta, that equal to Pe minus theta. This minus theta cancel. What we get now? I omega square. I omega square equal to Pe. Pe. See here, omega square equal to what now? Pe by I. See, omega equal to root of Pe by I. Pe by I. P means here electric dipole moment, E means electric field, and I means moment of inertia. So omega means angular velocity. Angular velocity. See, we know time period we want. Time period equal to what now? 2 pi by omega. Instead of omega, we can write this value, means root of Pe by I. So means we get, so time period equal to 2 pi into root of I by Pe. P means electric dipole moments, E means electric field, I means angular, sorry, moment of inertia. So this is the time period of oscillation of the electric dipole when it is slightly displaced from its stable equilibrium. See, whenever electric dipole is placed in the uniform electric field, that case it is in stable equilibrium, we slightly displace, that case it oscillates with small frequency, that case it is in simple harmonic motion. That case, what is the time period of this electric dipole, that we want find out. So for that, what not? Torque equal to Pe sin theta. Here small means small angle, which displays with means oscillate with a small frequency. That's why. So theta is very small. Sin theta equal to theta we can write. Instead of sin theta we can write minus theta. Why? Because displacement is this direction, torque is this direction. Both are in opposite direction, so we can write minus theta. See, minus theta now here torque means one more is there. I alpha, moment of inertia into angular acceleration. So I na angular acceleration is omega square theta. So minus omega square theta here, minus omega square theta. So Pe minus theta. See, omega square minus of theta, here minus theta cancel. What do we get? I omega square equal to Pe. We can write, means electric dipole moment into electric field. See, omega square equal to Pe by I. Omega equal to root of Pe by I. So time period equal to what? Actually 2 pi by omega. Time period equal to 2 pi by omega. Time period equal to 2 pi. Omega means this value, Pe by I. We can write time period equal to 2 pi into root of I by Pe. So this is the time period of oscillation of the electric dipole when it is placed in the uniform electric field and slightly displaced from the stable equilibrium. That case, what is the time period na? 2 pi into root of I by Pe. Root of I by Pe. See, one more, what now here, another problem. An electric dipole is placed in the uniform electric field. In this one, see here, I write here, this is the uniform electric field. Uniform electric field. This uniform electric field is 10 power 5 Newton per coulomb. What is the electric field now? 10 power 5 Newton per coulomb. Here electric dipole is placed. So this is plus q, it is minus q. This dipole length is 10 centimeter. What is the length of this one now? Sorry, 2 centimeter. 2 centimeter length. So dipole length is 2 centimeter and it is placed in the uniform electric field. What is the electric field now? 10 power 5 Newton per coulomb. What is the torque acting in this one now? Torque equal to 8 root 3 Newton meter torque is acting. This case, find the charge on electric dipole. Electric dipole, what is the charge on the electric dipole, that we find out. And another one is what is the potential energy, the two we can find out. See here, this is the electric dipole. It is placed in the uniform electric field of 10 power 5 Newton per coulomb. So length of this dipole is 2 centimeter. What is the torque acting on this one? 8 root 3 Newton meter. So torque equal to what actually? PE sin theta. PE sin theta. Here now angle is here, theta equal to 60 degrees. What is the angle now here? Theta equal to 60 degrees. This case, see tau equal to PE sin theta. So tau equal to P means Q into 2L into E sin theta. Sin theta means here 60, sin 60. See here, tau now here, tau what they give? 8 root 3. 8 root 3, that equal to Q value we don't know, 2L length we know, 2 centimeters. It will write it as in meters now 10 power minus 2 meters into electric field now 10 power 5 Newton per coulomb. So on the sin 60 means root 3 by 2. Root 3 by 2. This root 3 cancel. This 2 cancel. See here Q. This 10 power minus 2 now 10 power 5 is there. So plus 3 we get. It will be changes this side now 8 by 10 power 3, that equal to Q. See Q equal to 8 into 10 power minus 3 coulombs. This is the charge on the electric dipole. See once, so when electric dipole is placed in the uniform electric field of 10 power minus 5, 10 power 5 Newton per coulomb, what is the torque acting on the electric dipole now? Tau equal to 823 newtons meter. Find the charge on electric dipole and potential energy we want to find out. So for that here they give some information. So electric field and electric dipole angle is 60. Electric dipole length is 2 centimeter. Electric field and torque they give. So torque equal to P sin theta. So torque now P means Q into 2L, E sin theta value 60. So we can sin 60 now root 3 by 2. E value 10 power 5. L 2L now 2 into 10 power minus 2. Q same only. Torque now 8 root 3. Root 3 cancel. 2 cancel, we get what is the charge on the electric dipole na 8 into 10 power minus 3. We want to find out potential energy. So potential energy formula na, so potential energy U equal to minus of PE cos theta, minus of PE cos theta. So U equal to here C minus P means Q into 2L. So Q into 2L E cos 60. See here U equal to minus Q means 8 into 10 power minus 3 coulombs. 2L is 2 into 10 power minus 2. Electric field is 10 power 5 Newton per coulomb. Cos 60 now 1 by 2. See here this 2 cancel. Minus 2 minus 3 minus 5 is plus 5 cancel. What we get now? So potential energy is 8 joules. What is the potential energy when the electric dipole is placed in the uniform electric field? Now this is the 8 joules. So this is the solution. So thank you.